Welcome to Chapter 6 of our Cybersecurity series. I am Dr. Alaa Jabbar Almaliki from the School of Computing at University Utara, Malaysia, and today we are analyzing Intrusion Detection Systems, or IDSs. In modern networks, the threats are constant. Every minute of every day, external actors are probing, testing, and attempting to breach network perimeters. To stop them, we typically rely on preventive systems like firewalls. Did firewalls operate on strict binary logic? They sit at the edge of the network and simply evaluate whether incoming traffic is allowed or denied. Look at this network topology map. If an attacker disguises a malicious payload as standard web traffic, for example, routing it through an open port 443, the firewall sees an allowed protocol and lets it right through. Once that packet crosses the threshold, the attacker has free rein. The internal network is completely blind to what happens next. Relying entirely on a hard outer shell is a flawed strategy. We must engineer our security architecture with the assumption that the perimeter will inevitably fail. This requires a shift in how we approach defense. We need the capability to look inward, observing behavior inside the network, rather than just guarding the door. That is the role of an intrusion detection system. Think of an IDS as a dedicated sensory network deployed to provide real-time operational visibility into your internal environment. Unlike a firewall, an IDS does not actively block traffic. Its job is strictly to monitor the environment, detect suspicious activity, and generate alerts. Building a comprehensive IDS requires making engineering decisions along two specific axes of functionality. We have to decide exactly where the system listens, its deployment location, and how it evaluates the data it collects, its detection logic. By selecting the right parameters across these two axes, we turn an opaque, vulnerable internal network into a highly monitored environment. We will start with the first axis, deployment location. We begin by looking at the macro level of network transit. Here on the topology map, we place a network-based IDS, or NIDS, at strategic choke points. From this vantage point, it analyzes the contents of every incoming and outgoing data packet across that segment. Consider a scenario where external actors target the system with a distributed denial of service, or DDoS attack. The NIDS identifies the mathematically abnormal volume of traffic hammering the gateway, immediately triggering an alert. However, a NIDS has a major blind spot. If a single sophisticated packet slips through without triggering an alarm, the NIDS cannot see what it does once it reaches an individual target computer. It provides essential visibility over data in transit, but leaves us completely exposed at the local machine level. To correct that, we shift our engineering focus away from the broad network gateway down into isolated endpoint environments. This brings us to the host-based IDS, or HIDS. It's an autonomous monitoring agent installed directly onto individual devices, like critical database servers. HIDS examines metrics that the network gateway cannot see. It monitors local system event logs, watches active operating processes, and verifies the integrity of stored files. Imagine an insider threat, where someone with physical access or compromised credentials attempts a brute force login directly on the server itself. The NIDS at the perimeter wouldn't detect this, but the HIDS flags the behavior immediately on the local logs. It also catches localized malware. If a rogue process modifies a core system file, the HIDS detects the change instantly. A host-based IDS provides the granular, localized security required to catch threats that successfully bypass both firewalls and transit monitors. Now that we know where to place our sensors, we have to define how those sensors mathematically evaluate the data they collect. This is our second axis, detection logic. The first method is signature-based detection, relying on a historical dictionary of known malicious code. The system compares incoming files against this database, scanning for an exact programmatic match. Only when the incoming code perfectly matches a historical signature does the system generate an alert. The advantage of this methodology is efficiency. It is highly accurate at identifying recognized, documented threats. But the architectural flaw is significant. Signature-based systems are blind to brand new zero-day attacks. If the code hasn't been added to the database yet, it glides right past the filter. While it serves as a mandatory filter for historical attacks, relying entirely on signatures leaves the network defenseless against novel hacker innovation. To solve the zero-day problem, we engineer systems using anomaly-based detection. Look at this graph on the right. This logic relies on statistical baselining. The IDS observes the network to mathematically learn what normal behavior looks like, hunting for activity that deviates from this baseline. If the system registers a sudden, mathematically significant variation in traffic or behavior, it instantly generates an alert, regardless of whether it recognizes the code itself. This methodology allows the IDS to detect entirely new, sophisticated cyber attacks. The operational cost is that this logic is highly prone to false positives. A sudden, massive surge in legitimate user logins, for instance, looks mathematically abnormal and will trigger an alarm. Anomaly-based logic prioritizes catching everything new, but it requires heavy computational resources and active human analysis to separate actual threats from normal operational quirks. Bringing these concepts together during a live breach, novel malware bypasses the firewall. An IDS misses its signature, but flags its anomalous routing behavior. Reaching the server, it executes a known payload. The local HIDS immediately detects the unauthorized execution via a signature match. This reveals the true value of combined systems. They generate immutable security logs, recording every step of the attacker's lateral movement. These logs support critical incident response and forensic investigations, allowing security teams to understand exactly how the system was compromised. These systems translate chaotic network data into a definitive, actionable timeline of the cyber attack. Intrusion detection systems do not replace firewalls. They must work in tandem with them. A robust enterprise security posture requires the binary prevention of a firewall combined with the deep operational visibility of an IDS. By properly deploying both NIDS and HIDS and layering both signature and anomaly logic, organizations build the resilience necessary to survive modern cyber threats. This concludes Chapter 6 for the UUM School of Computing. Thank you for your attention.